my name is Changkun Ye. Today I would like to introduce our workbook paper, Label Shift Estimation for Class-Imbalance Problem, a Bayesian approach. This is the joint work collaborated with Russell Tsuchida, Lars Petersson, and Nick Barnes. To begin with, I'll first briefly introduce the class-imbalance problem. The class-imbalance problem is a widely known problem in the image classification tasks. The problem states that when sample frequency of classes is different between train set and test set, a classifier that performs well on the train set may not perform equally well on the test set, even if the classifier is able to generalize. An extreme case of the class-imbalance problem is the long-tailed classification problem, which have been widely studied in recent works. In our work, we proposed a novel model that is able to adapt a classifier trained on the train set in the source domain to a test set in the target domain without retraining or fine-tuning the classifier. We analyzed the class imbalance problem in a more general regime, the label shift problem. Label shift is a common type of distribution shift. Under label shift, the label distribution is different between the source and target domain, whereas the conditional distribution of the image given label is invariant between source and target domain. For example, the long-tail classification problem can be seen as the label shift problem, where the source domain have long-tailed label distribution and the target domain have uniform label distribution. In the label shift problem, we are given with labeled source domain data, a source domain classifier, and the unlabeled target domain data. The objective of the label shift problem includes detection, detect if label shift happens, estimation, estimate target label distribution, and correction, adapt the source domain classifier to target domain for optimal performance. We focus on the label shift estimation problem. We aim at developing a label shift estimation model that is effective in large-scale datasets and is robust to highly class-imbalanced label distribution, like long-tailed label distribution. After obtaining the estimate of target label distribution, we can use existing works to correct label shift without retraining the classifier. The more accurate label shift estimation model we have, the better target domain classifier we can get. We propose to estimate the target label distribution with a Bayesian approach. We observe that target label follows a categorical distribution. Estimating target label distribution is equivalent to estimate pi, the parameter of the categorical distribution of the target label. Thus, we propose to introducing an extra Dirichlet prior over the parameter pi in the Bayesian approach. Given the Dirichlet prior and other available data, we can construct the unnormalized analytical posterior of target label distribution. With the analytical posterior, we can either obtain a map estimate as the point estimate of the target label distribution pi, or we can use a Markov Chain Monte Carlo method to obtain IID samples of the posterior of pi. We derive an EM algorithm to obtain the map estimate of pi. We name our model as MapLS algorithm. We prove that the map estimate is unique, and our MapLS algorithm converts to the unique map estimate of pi. In the MapLS algorithm, we can rewrite the M step as a linear combination of two terms, the data contribution terms and the prior contribution term. The hyperparameter lambda determines the relative weight between the two terms. When lambda equals to 1, no prior information is used, and our MapLS algorithm will convert to the maximized likelihood estimate of pi. On the other hand, when the lambda equals to 0, our MapLS model will convert to the pi that is fully determined by our Dirichlet prior. Our MapLS algorithm requires that the parameter alpha of the Dirichlet prior to be given. In this work, we also propose the novel adaptive prior learning model to determine the prior parameter given data. We first simplify the problem. When no information of the target label distribution is given, we can just choose the uniform Dirichlet prior. In this case, we only need to determine a single hyperparameter alpha 0, or lambda, the weight of the data contribution term. Our APL model determines the hyperparameter lambda by first evaluating the three KL divergences: the KL divergence between the maximized likelihood estimate of pi, source label distribution C, and uniform categorical distribution 1 over k. We argue that the three KL divergences are correlated with the magnitude of sampling error or model misspecification error of our MapLS model. We adjust lambda to reduce the two possible estimation errors. After determining lambda, we can run the EM algorithm to obtain the map estimate of the target label distribution and then adapt a source domain classifier to target domain. Apart from the map estimate, we also propose to use a special type of MCMC, the Hamiltonian Monte Carlo method, to obtain IID samples from the posterior. The samples can then be used as an estimation of pi for downstream tasks. We test our model on a variety of label shift settings. Firstly, we train the classifier on several hundred ImageNet, places, and long-tail version of each dataset. Then we use our model and previous models to adapt the classifier on different test sets, including the direct set shifted test set, ordered long-tail shifted test set, and shuffle long-tailed shifted test set. The performance of the models are evaluated in terms of the label shift estimation error and top 1 accuracy of the label shift corrected classifier. As shown in the tables, in terms of the label shift estimation error, our model outperformed previous SODA models in at least 50% experiment settings. We also outperform other models in terms of the top 1 accuracy in a significant percentage of the settings. We also provide detailed results of some particular label shift settings. For estimation error, we outperform other models in most of the settings on ImageNet and long-tail ImageNet, as shown in the upper figure in the slides. For top 1 accuracy, our model outperforms other models on most of the settings on the long-tailed ImageNet and the long-tail places dataset, as shown in the lower part of the figure. We empirically justify the effectiveness of our APL model. As shown in the figure, our MapLS model with fixed lambda outperforms other models in many settings. Our MapLS model with lambda learned by our APL model can further reduce the label shift estimation error. We also provide the illustration of our posterior sampling model. We plot the histogram of the IID samples of the posterior of target label distribution of pi. Our posterior sampling model is valuable, especially when uncertainty of the label shift estimation result is important. In the ablation study, we report the label shift estimation performance of our model during the training of a source domain classifier. As shown in the figure, our MapLS APL model consistently outperformed previous models during the training of the classifier. That's everything I would like to introduce. If you are interested in our work, please take a look at our original papers, our posters, or contact me for further questions. Thanks for your attention.